So we have derived the expressions for the angular velocity, the angular deformation, strain rate, the vorticity in differential expressions of the velocity components. So if you know the velocity field, you can easily find out the other quantities. Now for a irrotational flow, rotational means existence of a angular velocity. The fluid is rotating with some angular velocity. But if it is a irrotational flow, the angular velocity components will be 0. All the three components will be 0. So the deformation of velocity potential function, sorry, the definition of the velocity potential function satisfies the irrotational flow. So we have defined the, now we will discuss the significance of the velocity potential function. We have defined the velocity potential function as u equal to del phi by del x, v equal to del phi by del y, w equal to del phi by del z. So now let's see, omega z, you know, del u by del y minus del v by del x. Now put u and v in terms of the velocity potential functions phi, del by del y del phi by del x minus del by del x del phi by del y. Now you see it's 0. So the angular velocity is 0. So if a velocity potential function exists in a flow, the flow must be irrotational flow. Yeah, if the flow is a irrotational flow, then velocity potential function exists. So when a stream function exists, already we have discussed. A stream function exists when a flow is a possible flow. When a flow is possible flow, if the flow satisfies the continuity equation. Now when a velocity potential function exists, when the flow is a irrotational flow. So for a irrotational flow, the velocity potential function exists. So you find out omega x, omega y, omega z. If all the three components are 0, then the flow will be irrotational flow. Now another interesting thing about the stream function and the velocity potential function are, they are the Laplacian functions of x and y respectively for a possible and irrotational flow. You see there are two quantities, possible flow and irrotational flow. Possible flow means existence of psi, irrotational flow existence of phi. So existence of psi means satisfaction of the continuity equation. So this is the continuity equation. Now put u and v in terms of phi. So this is 0. So what is this? Del square phi by del x square plus del square phi by del y square equal to 0. So this expression is nothing but the Laplacian of phi in 2D. In mathematics, you must have studied the Laplacian, okay, of any function. Similarly, existence of phi means irrotational flow. Suppose 2D, the flow takes place in xy plane, so omega z equal to 0. So what is omega z? Del v by del x minus del u by del y equal to 0. Now replace u and v by the use of stream functions. Okay, so u equal to minus del psi by del y, v equal to del psi by del x. So again you see it becomes del square psi by del x square plus del square psi by del y square equal to 0. Again this is a Laplacian of psi. So for a possible and irrotational flow, the stream function and the velocity potential function satisfies Laplacian of x and y. Now what is a flownet? So basically, if you know the stream function, you can plot the streamlines. So along any streamline, the stream functions remains constant. Similarly, if you know the velocity potential function, you can plot the velocity potential function curves, and along a velocity potential function curves, velocity potential function remains constant. So if you superimpose both the stream function curves as well as the velocity potential curves on a single plot, then that plot is known as flownet. Now what is the relation between the velocity potential curves and stream function curves? So we have to know the slope. Suppose on xy plane I will plot both the curves. So you have to know the relation between the slopes of both the lines. For a streamline, psi equal to constant and psi is a function of x and y. So find the total derivative. So d psi equal to del psi by del x dx plus del psi by del y dy. So d psi will be 0 because psi is constant. So from this you can find out this is the slope. dy by dx equal to v by u. Similarly, for a velocity potential function, phi equal to constant. Again, phi is a function of x and y. So find the total derivative d phi del phi by del x dx plus del phi by del y dy. So the slope is u minus u by v. The slope of the streamlines on a xy plane is v by u, and the slope of a velocity potential function on a xy plane is minus e by v. So what is the relation? The product of both the slopes will be minus 1. So when the product of both the slopes are minus 1, so they are perpendicular to each other. So if psi equal to c1, c2, c3, 3 streamlines, and phi equal to k1, k2, k3, 3 velocity potential curves, then you can plot. So these k1, k2, k3 are perpendicular to c1, c2, c3. So this is a flow net, typical flow net. So what is the significance of the flow net? So the if flow net exists, then the flow is possible and the flow is irrotational flow, because both the velocity potential function as well as the stream function exists. If a stream function exists, it's a possible flow. If a velocity potential function exists, it's a irrotational flow. So this is all about the flow net.